my name is Marius Filip, and this presentation is about business transactions on Ignite. And the content of the presentation, as you can see, I'm going to speak a little bit about myself. Then I'm going to move to the challenges that the commodity trading software has. And I'm going to speak about transactionality and what is the difference between a technical transaction and a business transaction, because this is the problem that we try to solve. And then I'm going to use our notification system, which is a small part of our platform, as a use case for the problem of business transactions. Then I'm going to go into more details to show how we can transmit information of Ignite in a transactional manner while keeping the consistency of business transactions, and how we can leverage Ignite to recover from errors, further developments that we envision, and some conclusions, and at the end, some questions and answers. Now, this presentation assumes a very basic understanding, knowledge of Ignite. There are notions like transactional rights or persistent queues or atomic longs that are going to be present. I'm going to try to explain very, very briefly what they are, but apart from that, the presentation is quite high level. Right, so I am lead for API and backend Java services with Amphora. Amphora is a company producing software for commodity trading. I've been in the financial sector in London for a little bit over the past decade, and I worked besides commodity trading also in investment banking and in retail trading. And I will refer actually to this experience a little bit. I will touch base that in my presentation. In my career, I wore many hats. I worked in various domains, and I can tell that this influenced the approaches that I get up to this day. And I got contact with in-memory computing about 5 years ago at a conference in London. And I got hooked into the concept very soon. And I've been pursuing since then events regarding in-memory computing. And I try to attend sessions and conferences whenever I can. And in all this mix that in-memory computing is, Apache Ignite is at the top of the list. And in memory-centric computing is I believe it is the next big leap in computing. We are in need for that. Before we have quantum computing or other advancements, the progress that we have in terms of CPUs, in terms of memory access, reducing latencies, and that combined with storage like solid-state disks makes in-memory computing, memory-centric computing, very, very appealing. So it's something that I kept advocating for quite some years by now. So I'm going to speak about challenges in commodity trading software. So commodity trading, yeah, it's trading of materials that we all need in all walks of life and in the economy. It is considered part of the financial sector, but it is at the fringe of it, in the sense not that it's less important or marginal, is that it touches in a deeper way other areas of business and of economy. Financial strategies make use of commodities. Gold, especially, right, is being used to stabilize risk, to control risk over financial portfolios. But trading in commodities happens because we need commodities in all sorts of industries, like in energy. We need coal, we need natural gas. In manufacturing, we need metals. In food production, orange juice, pork bellies, wheat, you name it. And transportation, again, fuel. And what is specific to commodity trading is it's very much tied to the physical world, and this has implication on software as well. And it's very ramified because commodity trading, this sort of trading models what happens in real life. Material goods that are being transported, that are being changed, they change hands, and they are being stored, and they are being transformed. It quite has ramifications, and in terms of what it's a business transaction, this has implications about how we have to develop software for it. So this specific nature of commodity trading has impact upon how we produce software for this area of trading. It requires significant business knowledge. You have to know what is going on in the real life, and as a result, it requires a strong business analysis team, and the software developers have to be good partners with the BA department. And because it models physical world and real life processes, what is actually happening and how the business understands the changes in the real world takes time to clarify. And as a result, the software may have to contain bespoke parts, not because the domain is not standardized or there are no commonalities, but because each trading house may do things differently. And this has the impact that the way we implement the software, the architecture and the design of the software has to take into account all these bespoke aspects. And in turn, when it comes to adoption, when it comes to the beneficiaries, the business using the software, it's a longer process because it takes time to clarify all these details that are not algorithmic. They are not. They represent what is supposed to happen in real life, plus the concepts that are built on top of it. This takes time. So even though adoption here is not about being able to sell the software, but is to help the beneficiary to use it. It's a slower process. And all these characteristics of commodity trading has impact not only on how we develop software, but on the technology itself and technological choices. One important thing is that the processes that happen, they are triggered by humans. It's something we learned. The trading house, depending on the case, if the trading house owns or manages the physical aspects, then if a ship with the material leaves a port, then somebody has to do it and to enter that piece of information. From that moment on, the systems, yeah, they can transmit the information, but the ultimate trigger is a human. And the consequences of that is technical problems that occur in other areas. High frequency, low latency, massive scalability are less of a concern because it's here we're not speaking about millions of transactions per second. Here we're not speaking about 100 million of hits per day. We're speaking about a very specialized software that manages large amount of money, large amounts of materials that represent important things, but by using a relatively small pool of highly specialized people. So technologically speaking, as I said, it's less of a challenge, but it's more of a challenge in how software is being developed, because you have to code the right thing. You have to you're modeling reality in software, and you have to get it right, even when the concepts are not very clear by nature, because they overlap. And I'm going to detail later on what that means by outlining the concept of business transaction. And business transaction will be the topic of the next slide. So transactionality, we know we use it all the time in technology. We maneuver it, right? But what does it mean from the business perspective? So I'm gonna illustrate that by putting the two concepts side by side. From the technical point of view, I have this little diagram, and yeah, the transaction has quite clear characteristics. Usually it's ACID. Distribution, yes, it's allowed, but it's quite well defined, and we know the participants into the transaction, like in a JTA or in a two-step commit, they know what they are doing, they know how to cooperate. Concurrent transactions, again, are allowed, but they are well spec'd. We have isolation levels, for example, in SQL. You know what to expect. You know when to use one or another, and it's quite clear. The transactional boundaries, right? You start with begin transaction, you end with commit, and as a result, the semantics of one transaction is quite clear, and it's unique. You know the bulk of operations that you want to go atomically to succeed or to fail, and this is what you get. Now, when it comes to business, situation is not quite like that. So I have here the trade cycle, this little diagram, and you can see by looking, this is a very, very simplified model. You can see that in no way this can be considered atomic, no matter how you try it. However, conceptually, from the perspective of the business, it may be that this represents a single transaction. So a transaction is rarely ACID, right? There is no, if warehousing here fails, you can't tell the ship to go back to the original port. There is no way to roll back. Alternatives have to be found. The phases between the phases that represent the transaction are scattered. There may be days between these two phases. Highly concurrent overlapping, and yes, a mine may extract ore for many transactions and for many customers into the same time. A ship may transport materials for multiple customers into the same time. And the boundaries of the transaction, what represents the transaction, is highly dependent on the perspective, on the business meaning, on the business actor that wants to consider the transaction. For example, here, is this shipment step, is it a transaction or is just a phase in the transaction? Well, it depends. It depends who looks at it. If even if the trading company, for example, uses a contractor for shipment, still the information that comes from the shipment company has to be integrated, or not, depending on the situation. Which means that a transactional operation from the business perspective doesn't have one single semantics, and there are other as I show here, other things to take into consideration, like, for example, side effects. Here we're speaking about trading, we're speaking about money. Profit and loss reports are essential. Now, what do you include in terms of profit and loss for a certain transaction? Do you include storage fees if there is a bad weather and the ship can go, and so you have to pay extra money for that? Then if you are insured, you don't lose money, but how are you going to include that? What if the insurance money come later? So how are you going to build the P&L then, right? So all these aspects in terms of timing, when we have technological transactions, timing is not an issue because we expect that the transaction is supposed to finish as soon as possible. No step in the transaction, in the write-ahead log, is going to wait for a certain, if it has to wait, if the condition is not right to carry out the step, then the transaction is going to fail and is going to get rolled back. Is not the same in business and in real life. Time is a problem. It has to be taken into account. Money, same thing. If I start in algorithmic trading, if I start a trade and it's going to take a few milliseconds, then I can guarantee that the exchange rate is not going to move by much during that time. Well, it's not the case here. From the time when I buy this and the time when I actually get paid, there may be quite a variability in terms of exchange and other things, because we're dealing here with physical world. The unexpected can hit. Now, usually these things are not included as part of commodity trading. They may be just a note or a document attached to an invoice or to a trade, but still all that information may have to be taken into account. So question is how, if the situation is so fuzzy and is so multifaceted, so how can we as technologists approach this idea of a business transaction? Because the business, they still want their notions to be presented to them, and they don't care about what is going on inside the system. They don't care about acidity. They don't care about all the other things. They only care that if I want to see this as a single operation, I want to see it. If I want to split it, I want to see it split. Now, so how it goes is, in a way, an emulation of what happens in technological transactional engines. What happens in transactional engines? You start the transaction, and usually there is a log that is being used to carry out the operations, essentially to maintain the state as the transaction advances, so that the state can be rolled back afterwards, right? It's not very unlikely, in a very, very simplistic manner, is not very unlikely what has to happen when it comes to business transaction. For example, here, if warehousing, if I come with my ship in the port and I can't warehouse it because there was a fire, okay, I have to find an alternative, or I may sell at dumping price the content, or do something else. So this is a failed transaction. Now I have to manage the state of all these phases. When it comes to the transactional boundaries, I have to have markers on my information that is attached to every single record, so that when I go over there, I can rebuild what the state of a certain transaction at any point in time is. So essentially, how we deal with that is to manage explicitly the state and to manage explicitly the identification, the information that identifies the business transaction. And when it comes to transactional boundaries, or to recover the state that represents this transaction for reporting purposes or for further processing, then it boils down essentially to what we would do in databases, to do the joins across those constraints. So this is roughly speaking how enrichment of the data is essentially in order to be able to respond to the various facets of how a business transaction can be considered. So I'm going to use as an more detailed example the notification system for our platform. It's a small but very important part of what we're doing. But it shows, it has the potential that shows what those business transactions are about. So we have Ignite cluster and we have trading system. When you see this, think of it like the legacy trading system. And let's see what goes in between. So in the trading system, there is a notification being sent. This notification is being received by a service fabric, and this service fabric loads data, which ultimately comes from the trading system, and aggregates it and sends another notification. And this notification is picked up by some builders, cache builders, that convert and collect the data and then save it in Ignite. And Ignite stores the information and notifies about changes to various consumers, listeners, but it does it by satisfying this transactionality. And in the next slide, I'm going to show a few characteristics of all this ensemble piece by piece. So in this notification contains only minimal transactional information. So this is business transactions. So it's those attributes that convey what a business transaction might be. And then this fabric is actually not a single service, it's a collection of services, each representing a way in which those transactions can be understood. Internally, we call them patterns. There are commonalities. It's not like you have to implement 10,000 services, no, but they are different. And if new ways of understanding and of grouping the information, of consider the transactional boundaries, then new services are being added. And the builders simply pick up this information and group it, because the information that comes out here may be flattened, maybe it has all the transactional information upon them, but they are not published in bulk. The builders, they group the information together and they pass it on to Ignite, and Ignite receives that and notifies the listeners transaction by transaction. Now, the reason this word transaction that appears all the time is the reason why we have all this, because Ignite, as we know, has very good importers. These notifications, these buses are Kafka. Ignite has very good importers directly from DB, data ingesters or from Kafka. So why do we need all this? And the answer is precisely in this transaction, business transaction. That's why it requires more complex logic to be implemented in order to cater for all these variability in terms of semantics, because the technological transactional model is not sufficient. The next slides, I'm going to show how, and this is the bulk of the presentation, how we ensure that this transactionality across Ignite from the builders, from the source, and towards the listeners is maintained. And there are before I move on to the next slide, there are a few requirements that are put upon this notification system, and especially upon this portion that is based on Ignite. And the first of all, no data has to be lost. Transactional boundaries have to be respected, and there is no the contiguity has to be maintained. when it comes to listening, Ignite has a very good feature. Probably you know about it. It's called continuous queries. And continuous queries are quite nice because they come with two guarantees. One is guaranteed delivery, and the other one is sequentiality. So if you make some changes in the order ABC, that you're guaranteed that you're going to get ABC on the other side, what you listen. However, these guarantees are not transactional. A transaction means I save a collection of records, then I should get back a collection of records. If I save collection A and collection B and collection C, then I should get collection A, collection B, collection C. This does not happen because the guaranteed deliveries, they are tied to the key in Ignite. Yes, you have those guarantees per key, but you don't have those guarantees across the keys. So let's see how we solve this. So we have these cache builders, right? That component that I said they construct the data that represents a certain business transaction. In Ignite, we have the concept of a transaction. It's a technological transaction. It has acidity, all the acidity properties. And on the listener side, there is a component that actually tries to ensure across keys the guarantees that Ignite gives per key. And let's see how that happens. So the builder starts by obtaining an atomic ID. This is one of the elements that I was mentioning. Ignite API has a function to generate sequences, to generate atomic longs. And then the builder opens up a Ignite write transaction, writes the data, then it uses a persistent queue that it will be used by the listening side, writes into the persistent queue, and commits the transaction. So once the data is written into the caches, also the data makes its way into the persistent queue. Now, the transaction waits to a certain semaphore that and then you places the atomic into a location that is being listened to by the listener as a continuous query, and then it signals the semaphore. So each transaction essentially there is a chain of semaphores that are being created, and the transactions, they listen one after another. Now, why this happens here and not happens inside of the transaction? Well, the answer is obvious, because we want the transactions to happen as freely as possible, as concurrently as possible, and to leave to Ignite to deal with that concurrency. But when it comes to notification on the other side, we want that sequentiality. And this atomic ID is also being used to check for contiguity. On the listener side, the listener has a query, listens to the changes on the atomic ID, the one that is being written at step 6 here. It picks up elements from the persisted queue, the elements that were populated at step 3. Then it applies upon the OVR, overlay counterpart of the caches. So in this solution, because the publisher and the listener, they work at very different speeds, we can't afford the listener to go and query the main caches, because they change while the cache is being running, right? So we have to have counterparts that are under the control of the listener. And now there are subscribed queries that can join tables, excuse me, right? And those queries are being run after the overlays are being applied. Each subscriber is being notified, and only after each notification succeeds, then the data is removed from the persistent queue, and the overlaid flag is set on this OVR area. So to give a very small example, let's say we have two caches, person and address, and we want to listen for this join here. we are interested in only these two fields. Now, what happens inside of the listener component inside of the system is that this query is being transformed into a query over the overlay, and is augmented with an overlaid flag that ensures that in the result set, only the data that has changed is being reported, is being included. And how come this overlay is set to true? Well, is because when picking up the data from the queue and applying it on the overlay, the listener component takes care to set this overlaid flag to true. And once the notification happens, then the overlay flag is being reset.
Let me quickly interject. Sorry, we only have a couple more minutes. I know we got off to a late start.
Yeah,
we'll try and stick to schedule. So
yeah, I'm gonna rush it up.
Okay.
Yeah. So when it comes to the recovery, I'm going to go very quickly. Ignite has a capability of recovering because we enable persistence, but there are a few points where the failed operation may produce problems. One is waiting for the previous transaction. If they didn't finish properly, then we wait forever. Well, we don't. If we can't transmit the ID on the other side, still the data is in the queue because it's being added as part of the transaction. And when it comes to publishing, yeah, the publishing may fail, and as a result, the reset will not happen. But that's not a problem because what's going to happen is we're going to notify duplicated data. The system that we have has guaranteed delivery at least once, but it assumes that more than once may happen. And when it comes to further developments, leveraging risk calculations on the Ignite platform is one way that we're thinking about, and we have very good presentations on this domain in this session. And the notification mechanism can be fine-tuned on particular cases when the query is upon one single table, for example. And obviously, Ignite has an extensibility mechanism that eventually we can leverage in order to produce a self-contained solution. So in conclusion, and I'm done with pretty much with the presentation. Commodity trading is has its own peculiarities that affect this developing of software in the domain. Business transactions are more complex, they are more multifaceted than technological transactions, but Apache Ignite offers a very robust computational model that we can build actual logic, business logic on top of it. And it is done by using very simple mechanisms that Ignite offers, like atomic values and persistent queues and transactional rights. So this brings me to the end, and I'm not sure whether we have time for questions.
We can take a couple of questions while I'm waiting for Rohit to join the stage, but we are literally on his time. So Rohit, if you don't mind, in the meanwhile, you can join the stage. So while he's doing that, Marius, thank you for your presentation. Thank you for your time. And it was a shame about the technical difficulties at the start, which kind of cut into your time today.
Thank you for having me.
No problem. It was a pleasure. In terms of the questions, I'm waiting on Marius to come, so I'll just quickly ask this one. You about the different types of transactions and what you mean by business transaction and Ignite transaction. How are you managing those boundaries between Ignite? In your previous diagram, you had a architecture diagram that showed where Ignite sits. How are you managing the transactional boundary there where it does matter from a technology point of view?
So yes, so the whole delimitation of the transaction, so basically the conversion from a business transaction to a Ignite transaction to a technological transactions happens in both the loader, but especially in the cache builders. That is their job, is to utilize that information and to build the data sets that are to be written transactionally, which is consistent with the transaction from the business perspective, on one hand. And on the other hand, on the listening side, the listener may have its own needs, so they utilize the joint, the listening to joint queries to say, this is what I'm interested in. From my perspective, that is the transaction that I will be notified about.
Perfect. Thank you for your answer. Again, thank you for your time.
Thank you.